Welcome to today's Explainer. We're going to unpack something absolutely crucial to mathematics. Imagine for a moment that the entire universe of math is built out of tiny, unbreakable atoms. Well, in the world of numbers, those atoms are called prime numbers. They are the absolute, irreducible building blocks of literally every other number out there. And figuring out how they work, it's not just some abstract, dusty theory. It's actually the fundamental engine powering advanced modern code breaking and global digital security. So let's decode exactly how these fascinating numbers operate.
Here's our roadmap for today. We're looking at four main pillars: building blocks of numbers, the rule breaker, which is number 1, hunting for primes, and finally, prime factorization methods.
Okay, let's jump right into section 1, building blocks of numbers, where we'll be understanding primes versus composites.
So our number system basically runs on a fundamental binary. On one side, you've got prime numbers. Think of these as those unbreakable blocks we just talked about. They have exactly two factors, 1 and themselves. That is it. On the flip side, we have composite numbers. These are numbers that can be shattered into multiple pieces because they have more than two factors. The really big takeaway here is that strict two-factor rule. That rule is the ultimate test of what makes a number a true, unbreakable prime.
Moving right along to section 2, the rule breaker, number 1 and why it is totally unique.
You see, mathematically speaking, the number 1 is a complete anomaly. It just doesn't play by the binary rules we just set up. Why? Because it only has a single factor, itself. It literally doesn't have the two factors required to be a prime.
And because of that strange reality, we arrive in an absolute ironclad rule. 1 is neither prime nor composite. It is an entirely unique exception sitting completely outside the system. Kind of a lone wolf, really.
All right, on to section 3, hunting for primes. We'll look at ancient algorithms and a few even oddities. Now you might be wondering, how do we actually find these prime atoms out in the wild? Well, to answer that, we have to travel back over 2,000 years to a brilliant Greek mathematician named Eratosthenes. He came up with this remarkably clever tool called the sieve of Eratosthenes. Think of it like a physical sieve you'd use for panning gold, washing away the dirt to leave only the precious nuggets behind. Well, he created a mathematical version of that to filter out all the composite numbers and leave behind just the pure primes.
Just imagine a giant grid of numbers, say from 1 to 100. His algorithm is brilliantly simple. Step 1, you cross out the 1, since we know it's not prime. Step 2, you circle the 2 and then systematically cross out every single multiple of 2 because they're all composites. Step 3, you move to the next available number, 3, circle it, and cross out all its multiples. You just let this cascade forward, repeating the process until every single number is either circled or crossed out, leaving you with a grid of pure prime nuggets.
And right away, this sieving process reveals an amazing piece of mathematical trivia. 2 is the only even prime number in existence. Think about it. Once you cross out all the multiples of 2 in that first step, every other even number completely vanishes into the composite pile. No other even number stands a chance.
So let's test that out. Think about a number like 10. Why exactly is 10 considered a composite number, even though it's an even number?
Well, any even number greater than 2, like 10, basically carries a structural guarantee that it's composite. Just look at its factors, 1, 2, 5, and 10. It will always be divisible by 1, itself, and 2. Because it has those extra factors, it is mathematically impossible for it to remain a prime atom.
Okay, let's try another one. What about the number 13? Is it a prime or a composite number?
It's absolutely prime. Its only factors are 1 and 13. You cannot divide it evenly by anything else. It perfectly fits our unbreakable two-factor requirement.
Let's wrap up with section 4, prime factorization methods, or how we break numbers down.
If primes are our atoms, prime factorization is basically mathematical chemistry. It's the process of taking a complex composite molecule and deliberately breaking it back down into its base prime elements. And we generally use two common methods to do this: factor trees and the division method.
Let's look at a factor tree first. Take a number like 30 and fracture it. We split it into 3 and 10. Now the 3 is already a prime atom, so we circle it, and that branch stops. But the 10 fractures further into 2 and 5. We circle both of those, since they're prime, gather up those endpoints, and boom, we've successfully reduced 30 to its core DNA, 2 times 3 times 5.
The other approach is the division method, which acts a bit more like a chisel. Take the number 18. Chisel it by dividing by the smallest possible prime, which is 2, and you get 9. Now, chisel 9 by the next smallest prime, 3, to get 3. Divide that by 3 one last time to reach 1. Those tools you used to chisel it down, the 2, the 3, and the other 3, those are your prime factors. So 18 breaks down to 2 times 3 times 3. We've just seen how simple it is to break down smaller numbers like 18 or 30. But here is the mathematical one-way street that literally secures our modern digital world. Multiplying two massive prime numbers together is practically instantaneous, but taking a massive, hundreds of digits long composite number and factoring it back into its prime parts, that is incredibly difficult for even the fastest computers. So it really begs the question, if primes are the building blocks of all numbers, what massive composites are waiting to be cracked in today's advanced code breaking, and just how big do these prime building blocks really get? Well, that's something to chew on. Thanks for joining me on this explainer, and keep exploring the amazing DNA of math.